got to do the same exercise that I just did with you, okay? But you have one more difficulty in there. You have to recognize something. That's the entropy change. You're done. Okay, good. Good. All right. Okay, there is some tendency towards A, but there are quite a few people. You see, it always happens just the day, 1 or 2 days before spring break. There are no more D's and D's. These guys are already at spring break. Okay. Of course, now I'm going to get a lot of D's and D's. Anyhow, this is just my observation on the side. So let's look at this. I'm just kidding, of course. Yeah. Let's just look at this here. You have the delta G was 25, was spontaneous at standard temperature. And what do you have? You have a dimerization. What happens to your entropy here? This here and this here. So you have 2 moles here and 1 mole here. What happens to your entropy? With this, you have your entropy term, the change in entropy. And now you can discuss it with each other and try to give me a more correct solution. So what is it? Good, excellent.
I did part of the already, but I'm not entirely sure. Where did you put values?
No, you need to find it out from this picture what's in it. You don't need any value.
Why don't you give me that?
You need just look at the picture. What's the difference?
Okay, that looks like the same one you did the other day.
Yes, you're getting it. Very good. Excellent. I asked for it. Okay, good. So what the key is, the first thing is it's spontaneous. That means delta G is negative, all right? And the second thing is you have a dimerization. So which one has more order? This one or that one? Okay, so what is delta S then? Delta S is smaller than 0, is that right? So you go from dimerization, so you go from 2 moles to 1 mole. So you have less microstates here. You have more order. Delta G is delta H minus T delta S. It has to be smaller than 0 because it's a spontaneous process. And we see here the delta S is smaller than 0, but this here. Minus T delta S becomes, if this is negative here, that becomes positive. It's larger than 0. That means delta H has to be negative in order for delta G to be negative. And this was your correct answer. I love it. Very good. So let's make it a little more difficult. Now we're plotting, remember our water example? We're plotting delta G versus the temperature. Delta G versus the temperature, okay? Now you have liquid water going into gaseous water. Of course, this only happens if you increase the temperature, all right? So obviously there's an increase in temperature and something happens to the free, it gets free energy here. And I'm asking you now, if you go for delta G versus temperature, when you go from the liquid to the gas phase, the liquid to the gas phase was you increase the temperature, whereas our liquid phase, liquid to the gas phase would be this here, okay? All right, so why don't you think about this and see, actually that's a linear equation also. You can do it this way or you can reason it. So just imagine liquid water sitting here. Is delta G negative? No, okay, that's the first step. Now then you increase the temperature, what happens to delta G? Are we in the discussion already, or is that discussion already? Yeah. No? Okay. The first one you got to do by yourself, okay? Or you talk about Mexico, what's going to be there. Who's going to Mexico? You see, good. Not that many. Don't get kidnapped. Okay, there is some kind of a majority trend. If you agree with this, you vote for this. If you disagree with this, you vote for something else. So now you have water sitting here. Is this a spontaneous reaction to go into the gas phase? No. So delta G's got to be at lower temperature, has to be positive. Is that right? Okay. With this, I think I gave everything away already. So why don't you think about this? And now you can discuss it quietly. No. Please discuss it with each other. It's important that you get that. It's very, very important. The midterm will have a lot of calculations, and you need to understand this. Absolutely. Everything till Friday before. We do. Yes, my wizard. You're good. I'm very happy about this. Even if you voted, some of you voted with the majority, but a lot of you understood it. And of course, delta G is not negative if the water sits right here at room temperature. If you increase the temperature, okay, then what happens? If you increase the temperature, it becomes negative. It's positive at the beginning, so this would be negative. Forget it, okay? Now what happens with this one, if you increase the temperature, delta G becomes more positive. That's not right, okay? The water really, if you boil the water, then it will have delta G negative. With this here, delta G negative, this is our equation here. The intercept is delta H here, okay? And this T times delta S, okay? Delta S is your slope. And with this you get delta S is you produce gas that is larger than 0. Delta H is the next endothermic reaction because you have to put in heat in order to make the gas. And so the slope is negative. Of course, we have that here. The slope is negative. And the intercept is positive. That would be this here. And this is the right answer, as you so many of you had correct. So if you just to look at this, is there an entropy of 0? Is there any compound that would have an entropy of 0? No, exactly. No is the answer. Theoretically, there would be a compound where the entropy is 0 if we could reach 0 degree temperature, absolute 0. Okay, that means you would have a perfect crystal where all the atoms in the crystal lattice are sitting on their lattice places, and there would be no movement or anything. With this, the entropy would 0. You never can reach it. But solids have low entropies. You see here carbon, for example, and there's an absolute entropy. All right, there's not like we said it here that this is a state of comparison. Okay, the entropy for carbon, for example, is 6 joules per Kelvin per mole. You see that here, delta H is in kilojoules and delta G is in kilojoules, but this is in joules. Okay, so be very careful when you do your calculations. Now, the solids, they have relatively small entropies. If you look at the gases, they have 200 and 161, and the liquid is, as compared to where's solid water? I don't have frozen water. The liquid has 70 joules per Kelvin per mole, and the gas 190, 189 joules per Kelvin per mole. You see that? But make sure that you understand this is a very small number in terms of joules per degree per Kelvin per mole. Now, we have to go through this experiment now. We say potassium and water makes K plus ions, potassium ions, and OH minus ions, and gas. So what happens? And this is, you've seen, remember, we've thrown the potassium into water. It was what? Exothermic or endothermic? Oh, thermic, exactly, exothermic. And exothermic, and when if you look at this, you have a solid and a liquid, and here you have a liquid and a gas. What would be the change in entropy? Positive, wouldn't it be? Okay, that was exothermic. The change in entropy would be positive. With this, delta G would be what? Negative, okay? That goes in this direction. Now let's do the next one. We have liquid, water, and oxygen. So it's a liquid and a gas, and that's a liquid. And so we don't know what the enthalpy change is. I have to tell you that. The enthalpy change is positive, so it's endothermic. You have to put in heat, okay? But you know what the entropy change is. The liquid and the gas, it becomes a liquid. So what is it? Negative, okay? And what would be delta G then? At room temperature, or at all temperatures, would be positive. And that means that reaction doesn't go that way. But we can go in the opposite direction. We let it go in the opposite direction. We say H2O2. We make oxygen and water out of it, and we have H2O2 here. And we have H2O2 here. And so we have a catalyst, a manganese dioxide catalyst. That catalyst takes apart the water. And if Karen does this now, you should see what this reaction is. That should be exothermic, shouldn't it be? Aha, this is steam, warm steam, and oxygen. Ah, okay. All right, so in the opposite direction it was spontaneous, but in the direction we have written it, it's non-spontaneous. Now let's look at the next reaction. We have here aluminum. I think we do this the next time. Yeah, because then we are the same with the class. We have aluminum, and aluminum bromide is a solid, and this gets into a solid and a liquid. So what is the change in entropy? Is it positive or negative? So this is ordered, this is less ordered, isn't that right? So that's positive, and the enthalpy change is positive, so it's endothermic, and it's also the entropic change. So now, where would that work? No, I don't need that here. I need that here. Where would that work? Would it work at high temperatures or would that work at all? So this is positive and this is positive. So that means, so it would work at high temperatures. It wouldn't work at low temperatures, but it would work at high temperatures. So at high temperatures it would work, at low temperatures it wouldn't work. Okay, so that would be negative is at high temperature, at low temperature it's positive. So we can do this in the reverse direction. The next time we use aluminum foil and bromine liquid. You have seen bromine before. I erased bromine, and we make aluminum bromide. And then we come to the last reaction where we have magnesium. Now this is difficult to say. Magnesium is a solid, and we have solid carbon dioxide. We make magnesium oxide and carbon. Okay. So what would be the entropy change of this here? We don't know, okay? So it could be so from just looking at this, but I need to tell you what the entropy change, the enthalpy change is. That's negative, okay? That's negative, and the entropy change is also negative. So if this is negative here, this is negative, okay? And this is negative, so this becomes positive then. This becomes positive. At what temperatures would that work? At low temperatures. And the nice thing is, we have carbon dioxide has a low temperature. Already a low temperature. It's frozen CO2 is carbon dioxide, and this is what Karen's going to do. She puts a magnesium, solid magnesium, on a block of carbon dioxide, and then puts activation energy on it, and then the reaction should happen at cool temperature. Not very logical from what we understand, but if you use these equations, then it will work. Let's see if this works. That's a cool experiment, to speak. You can take all the time you want. You won't see that often. So now we're trying to get the activation energy going until the reaction starts. It'll take a little while. No, there's no popping. Yeah, it is a flame. It makes it hot. Yeah, but just wait. That's the activation energy. Okay? Just wait. Now, wait. Okay. Isn't that something? Fire and ice. The yin and yang of chemistry. You've seen it at Chem 1A. Free energy gives free energy at its best here. Okay, there it goes. And there goes our lecture for the next guys. All right. Fire and ice. And with this, I'll see you on Friday.